Good afternoon, everyone. So thanks for coming to this group meeting again. And today we will have a presentation by Maria Jose called Characterization of Three-Flavor Composition of Cosmic Neutrinos. Let me check if it's okay. Okay.
Hello everyone, today I will be talking again about neutrinos, in this time about some results of the IceCube collaboration, about the characterization of the three-flavor composition of neutrinos. So let me start by presenting you the IceCube experiment. IceCube is in fact the biggest neutrino observatory in the world. It is located in the South Pole in the Antarctica, and it brings scientists from around the world together to make astronomy research. Astronomy research with high energy neutrinos. And you may be wondering, why do they use neutrinos instead of photons that are easier and cheaper to detect? And well, actually, this is because neutrinos interact much less than photons, so they can travel longer distances without even without interacting with any particle in the way to us. So they bring direct information from their sources. IceCube uses more than 5,000 of digital optical modules or DOMs that are these spherical detectors you can see here or here, and they are distributed along these long lines, long strings, that can reach up to 2,450 meters under the ice. So these domes detect the chunk of light produced by the charged particles that are created in the neutrino interactions. And know that even if they are trying to detect high energy neutrinos, our current detectors are still unable to detect them in a direct way. They just can detect the products of their interactions. Because of the low interaction of the neutrinos, the only way to prove the cosmic ray production and acceleration mechanisms is by using the neutrinos, and particularly by measuring the flavor composition of them. And this is basically the main goal of the paper and the main goal of this measurement of IceCube. So because of this, IceCube has been taking data since the 2013 until now of the global flux of the high energy neutrinos. And I'm talking about global flux because they are not measuring a particular direction or a particular source. They are measuring like the global flux. Well, they also perform some point sources analysis, but for now we're just talking about the global flux. Well, as you may know, the neutrinos come in three different weak flavors that are able to oscillate or to change while the neutrinos propagate through this space. And this is basically because the weak eigenstates are linear combinations of the mass eigenstates, and they are related by the PMNS matrix, as you are seeing there. This is important to take in mind because if we want to measure the composition of the neutrinos of the sources, it is going to change when they arrive to the Earth. But that is not a problem at all because we can perform like kind of a conversion to find the flavor fraction measured in the Earth given by this left term. By knowing the flavor fraction in this source, by applying the probability of oscillation that is here, and that is going to be given by, of course, related by the PMNS matrix elements, as you are seeing here. These three of here are the main neutrino production mechanisms of these astrophysical events. So as we're about to see, each of them produces a different neutrino flavor compositions. First of all, we have the pion decay that is going to produce a muon and a muonic neutrino. Eventually, the muon is going to decay into an electron, an electronic neutrino, and a muonic neutrino. So it will result in a composition of just one electronic neutrino, two muonic neutrinos, and zero tauonic neutrinos. This is by seeing in the source and by taking in mind both processes. Also, I want you to know that we are not bothering about differentiating the neutrinos from the antineutrinos because ice cube cannot distinguish them. So we are just counting their flavor.
So, sorry, these are coming from cosmic rays?
No, from like any specific any astrophysical source. Like those are the main production mechanisms. In second place, we have the neutron decay that is going to produce just one electronic neutrino, as you're seeing there. So this is going to be the flavor composition. And finally, we have the muon damping that, as you can see, it's the same pion decay process, but now with the assumption of the existence of a strong magnetic field that is going to make the muon lose enough energy to suppress its decay. So this is because of synchrotron emission, and so the muon is not going to decay, and we are going to have just the muonic contribution to the composition. Well, as I was mentioning at the beginning, Ice Cube detects the neutrinos through the charged products of their interactions. So we're going to see that each flavor neutrino is going to produce a characteristic morphology signature in the detector. First of all, we have the cascades that are produced by the charge current interactions of the electronic neutrinos that produces electrons. So because of the tiny mass of the electrons, they are quickly slowed down and absorbed by the ice. So they are going to produce compact signatures in the detector as you're seeing there. Well, in that illustration, each bubble represents a heat dome, and the sizes of the bubbles represent the amount of light produced in the dome. Also, the color characterization has to do with the time of the heat. So the color red is for earlier uh, hits, while the green color is for later hits. In second place, we have the tracks that are almost always produced by the muons of the charge current interactions. And because of they have higher masses, they are able to travel longer distances and barely and they don't interact with they are able to travel longer distances without even decaying or being absorbed by the detector. So they produce this like a continuous track in the detector. Finally, we have the double cascades that are produced by the tauons that are generated by the charge current interactions of the tauonic neutrinos. In this case, the first cascade is going to be produced by the hadronic part that is created together with the tauon, and the second cascade is going to be created by any of the particles that in which the muon can decay in. It could be muons, could be electrons or hadrons. Well, the main sources of background are atmospherical the main sources of background that IceCube has are the the atmospherical muons and the atmospherical muonic neutrinos. And because of this, IceCube has vector regions in charge of exclude the events that are produced outside a detection region. However, this works very well for the muonic background, but not for the neutrino background. And so for this, they need to exclude, they need to reject the events with neutrino energies below some threshold, below some energy threshold, having in mind that, of course, the atmospherical, sorry, the astrophysical neutrinos have higher energies than the atmospherical ones. Well, so then they split the data into the three morphologies: the cascades, the tracks, and the double cascades. They plot the fluxes into histograms depending on the energy, the direction angle, and the distance between cascades. This one just for the double cascades, of course. And here I'm just showing you the histograms of the double cascades. But if you want me to show you the histograms of the cascades and the tracks, I have them here too. Well, they also perform a Monte Carlo simulation. They perform Monte Carlo simulations based on some theoretical models. And here they are showing them with these colored lines you can see here in the histograms. Well, actually, those Monte Carlo simulations are made for every possible neutrino flavor combination or composition, and that is because they perform a maximum likelihood fit that compares the simulated data with the measured data, and so uh, they are searching for the best for the flavor composition that maximizes that likelihood fit. So that would be, in other words, that would be the flavor composition that makes the model best reproduce the measured data. In that combination, that flavor combination will correspond to the best fit. Here I'm showing you the results, the IceCube results. You can see here in this part the best fit they found after this analysis, represented by a little star. You can see it here in this triangular plot, which axes are given by the flavor, the neutrino flavor fraction measured in the Earth. And according to the best fit they found, they can plot the 68. They plot the 68 and the 95 confidence regions. Also, they show here the 68 confidence region found in the last measurement in the 2022 with the dotted line. And also, you can see here an irregular and dot 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 dash dotted line sorry, dash dotted line here, and it encloses the region with all the possible flavor combinations, um, all the possible compositions of the flavor neutrino coming from standard oscillations, and this is regardless of the composition of the original source. So this region is kind of easy to obtain. It is just by making the sum of the fractions equal to 1. So what does that mean? Basically, if we find some measure outside that region, it will correspond to a measure. It will come basically from non-standard oscillations. So that is like the crucial point in the interesting point in here. So basically, see, if the measure falls outside the region, it will imply new physics. Also, you can see here the marks of the neutrino mechanisms we were talking about before. The pion decay is the circle here. The the neutron decay is the square, and the pion decay is the triangle. And as you can see, they fall all of them fall inside the region, showing that in fact correspond to standard oscillations. And also you can see here how close is the best fit to the pion decay mark, that is this circle. So with this, we can assure that in fact the flux measurement of ice cube was strongly dominated by the pion decay mechanism. And well, to conclude, we have seen that the neutrino flavor composition of the ice cube measured fell into the standard oscillations region and show that was strongly dominated by the pion decay, and also that the future measurements of ice cube can bring relevant information about new physics. And that's it. Questions?
I do have a comment that I saw a talk by Hausen, he's the leader of Ice Cube, and he said you can apply for staying for a few months in the South Pole if you want to. You just enter their website and you fill a form if you want to go to the South Pole and check some of the. And they need someone in the computer or something, some lab work, and then you can spend like a month or two.
I have a question. I don't know if you could come back to the plots with
Which plots? This one or this one?
This one with the plots. Well, actually, the question is the other plot. They use a lot of Monte Carlo simulation, and they do comment in the references that you use the accuracy of the method, because you have extensive error bars of the experiments. So Monte Carlo simulation has its own error depending on the model they are using. So they have this kind of information.
But I think the error bars also depends on the initial flux, because this is something that is coming from the universe. We don't really know about it.
Yeah, that's my question, because a lot of things can fit in that.
Yeah.
So when you're going to analyze the portion of the plot that came from the atmosphere, in the simulation, you need to have some constraints on the simulation to have the accuracy. So that's my question.
Well, actually,
They do not comment or comment something
okay.
like that. So that's
Yes.
the question.
Yes, because like I didn't went too deep into the Monte Carlo simulations data. So
Okay, just do it for clarity, because it's an interesting evaluation. There's a lot of sources of errors in the experiments, and
Yes,
in the
that's
model you
correct.
have to select for that. So just question.
I have a question on this.
Excuse me.
Hi, Ricardo.
Sorry if I was not paying attention because I'm in the train right now. But when is this paper coming? When is this paper? The date?
When is it from the paper?
When is this
What
date?
day? The date.
it is from October of
Yeah.
October. It's
this
recent.
year.
This
It's recent.
year, right?
Yes.
I perguntou qual era a data.
Okay.
I have a question on this slide as well. You say that the main background noise is on muons and
Mm-hmm.
muon neutrinos.
Yes.
Is there a background to the signal for electron neutrinos?
Is there what? Sorry.
Is there a background as well for the signal of electron neutrinos and tau neutrinos?
No, the main background are from just from the Munich part.
I think the
I think-
flux is much greater for me.
Yes, and I think that is because as the detector is under the ice, the electrons, for example, are absorbed. So,
Okay, they are filtered for the.
and I think the tau ones are not too much produced as the muons and the electrons.
It's because in this three plots, the dashed black line is atmospherical neutrinos.
The black the black dots are the data, the flux.
Experimental data.
The
No,
yes,
the gray one.
She's speaking
The
about
dash.
the dash line.
Yes.
the
Right?
gray one,
Dash line.
the gray
Yes.
one. Yes,
No, that is measured as atmospheric conventional.
the atmospheric neutrinos.
Oh, sorry. What's the difference between these three plots?
Oh, sorry. It is the
G.
one is in terms
Oh, okay.
yes,
okay,
the,
right.
exactly.
Oh, never mind. All of them are in the scales. Okay.
Your question on muons. So we have something in the atmosphere that produces an electron. It will stay there, right? It won't reach the detector.
Yes, it also.
If it produces a muon, it can reach the detector. So if you
Mhm.
make a detector here, you can detect atmospheric muons. It's a very large flux.
Yes.
And the muon, one of the main channels of them became the muon neutrino and then electron and muon. So this new mu is coming from this, I think, from the decay of the muon. Right?
Yes, I think so. I have the histograms of the other morphologies here if you want to see.
Because you want something that is from
Yes, there you have the atmosphere muons.
the number of muons is much larger.
Yeah, I got confused because I thought that three plots was for three.
No,
like
no.
processes, but it's three.
And tau is
Depending
very
on-
short-lived, so
Oh,
it doesn't matter.
it's very messy.
And it's short-lived.
Yeah.
Even on LHC, you cannot see tau. It will decay.
Yes.
So there isn't any more questions. Let's take the speaker again.
So thank you all for being here to the presentation and see you next time. Me and the stream.